Okay, we're going to try to see if we can prove one more theorem or idea about congruence. There is a property of equality for which there is not necessarily a property of congruence. There's a substitution property of equality, but there's not a substitution property of congruence. What I want to see if we can do is see if we can prove, even though it's not a property, if we can kind of come up with some idea about congruence that we can use kind of similarly to how we would use substitution. So let's take a look at substitution real quick. The substitution property of equality basically says if two things are equal to each other, you can replace it in a statement and that statement is true. So for example, if I have this statement x plus y equals 30, but I know x equals 2, what I can do is I can replace that x with a 2, right? And I can say just, okay, 2 plus y equals 30. And then if I wanted to, I could go through and solve for y, right? Subtract 2. That's a property that we use in algebra when we're solving equations. So that's the substitution property of equality. Now, if we kind of take a statement like this and we turn it into segments or segment measurements, it would look something like this, right? So, and we actually used this already in one of the proofs that we did last week with a midpoint and stuff. So if AB plus BC equals AC, that we would get that from like a segment addition postulate. But then we knew that like AB and BC were actually equal because B was like the midpoint of AC. So let's say we had something like this, right? So AB and BC are equal to each other, but also AB plus BC equals AC. Well, what I could do is I could take this original statement and I could just rewrite it AB, AB, right? But instead of BC, I can replace this BC with AB because they're equal to each other and have that equal AC. We used that in a proof last week, and then our final statement was 2AB equals AC or something like that. So that's kind of how that substitution works when we're talking about segment measurements. This is kind of like what we want to have though, and this is what one of the properties that we don't really have for congruence. We want to be able to say that if AB is equal to CD, so some segment is equal to some other segment, but that same segment is equal to a third segment, then these two segments have to be equal. That kind of looks like the transitive property, but notice that the order is off. I'm not going AB to CD and then CD to EF. I'm going AB to CD and then that same one. So 1 to 2 and 1 to 3, and then saying 2 and 3 are equal. Now with the substitution property of equality, that's totally fine. That totally works out. That's no big deal, because if I know that AB is equal to CD, I can replace this AB with CD, right? So I can jump from this statement to this statement and say these are equivalent. Oh, excuse me. Sorry. Since we already know that AB is equal to itself, then these two have to be equal. That's a substitution property of equality. Now, it'd be kind of nice if we had that for congruence, because we could get around the transitive property. The transitive property only works if the order is right. The end of the first statement has to be the beginning of the second statement, or the second segment of the first segment needs to be the first segment of the second statement. Sorry, let me say that again. The second segment of the first statement has to be the first segment of the second statement. So it has to be like AB to CD and then CD to EF. That's how that one works. But here the order's off, right? I have AB is congruent to CD and AB is congruent to EF, and we want to say that CD and EF are congruent. That's not the transitive property, although it looks very similar. But I think we can prove this by using some properties of equality, okay? So if we can prove this, then we can kind of extend our transitive property so that the ordering doesn't have to matter as much. And we're going to call this the segment congruence theorem. So the idea here is if two segments are congruent to the same segment, so if two segments, these two guys, are congruent to the same segment, then these have to be congruent to each other. That's what we're going to try to prove here. So we're going to jump over here to our proof area, add our little 2-column guy, so statements, justifications, and we're going to have our given statement is just going to be this piece, right? So given, we have some segment congruent to a second segment, and that same segment congruent to a third segment. And we want to show that the second segment and the third segment are congruent to each other. We want to show that AB has got to be congruent to EF. Okay? And I think we can do this by using the substitution property of equality. We just have to use the definition of congruence and combine that with this property of equality to be able to get this theorem here. Okay? So let's start with the first statement. AB is congruent to CD and AB is congruent to EF. Given. Okay? The next thing we're going to do, and this is pretty common in a proof if you have a congruent statement, is to switch it to an equality statement using the definition of congruence. So the very next statement would be AB equals CD, and AB is also equal to EF, right? And that's the definition of congruent segments. Definition of congruent segments. That's what we get there. Okay. Now, from here, we could pretty much invoke our substitution property of equality if we wanted to. We could just say, hey, look, they're both equal to the same thing. We could maybe even add another line where we say AB is equal to AB because of the reflexive property. But I think, from this point, we have two things equaling the same thing. So that would be one of Euclid's common notions, or like the substitution property. Two things that are equal to the same thing are also equal to each other. So we're just going to say CD is equal to EF, right? And we'll use the substitution property of equality, okay? Which is kind of like one of Euclid's common notions there. Now there's some more things that we can do with substitution that we probably can't apply to congruence, because we wouldn't have like an equation kind of thing with congruence. Pretty much when you're talking about congruence, it's like two things congruent to each other at the same time. You don't have like chains of three things, or you don't have like equations with congruence. So these things probably don't apply as much, but this is the idea, this is the piece that we're trying to copy over to the congruence side. And we're pretty much there, right? All we got to do is just, we wanted to prove, I put the wrong statement. We wanted to prove that the second and the third guy were congruent. Sorry about that. We already had that statement. So AB is congruent to CD, AB is also congruent to EF. We want to prove that CD and EF are congruent, which we basically just did here, right? So CD is congruent to EF. And how do we know that? Well, again, that's the definition of congruence. If two segment measurements are equal to each other, we can say they're congruent to each other. Boom, we got it. So we pretty much